Alright, so in this video we're going to be going over extrema and inflection points. This is going to be 5.3 for the calculus notes. So I guess to start off, we got a question. Hold up, let me move this. What does it mean for a function to be increasing or decreasing? So the easiest way to think about this, in my opinion, is you could say from left to right on the graph, the y value of the function is going to be increasing. So correspondingly, it looks like it's increasing. Now, correspondingly, you may think as well, from left to right of the graph, if the y value is decreasing, that must mean the function is also increasing. Now, if you want to get into the actual formal definition of what it means for a function to be increasing or decreasing, what it actually means is that if you take your derivative of f of x and your value, right, of the derivative of x, remember that your derivative of f of x is just your slope of your function. If it's greater than 0, then that means that your function is going to be increasing. And if you take your derivative of f of x and your function is less than 0, then that means that's going to be decreasing. Now, graphically, if you look at this, to start off, for an example, we use, say, x cubed, right? And x cubed, it kind of has like this little wiggly pattern. And so let's go with blue here. Say if we take a tangent point, say here, and then we'll take it here, right here, I'll keep doing it. Other than that, when x is equal to 0, because we know with x cubed, when x is equal to 0, our tangent point for its slope is going to be 0. So I'll talk about that in a minute. But if we keep on taking the slopes of this, you'll kind of see here that all the slopes are going to be positive values, right? So what that is going to mean is what I talked about right here. But I'll get into this now. With functions like this where it flattens out at right here, and this is going to be at 0, our derivative of the function is actually equal to 0. So what this also includes is that when the derivative of f of x is going to be greater or equal to 0, it's going to be increasing, and it's not decreasing, right? So essentially what I'm trying to say here is, like, with a function like this, you have to just make sure that you put the bounds as it's also equal to 0. Correspondingly, it's also the same with, what's it called? Negative x cubed, but it's opposite. You can see here that if you take tangent points at any point on here, the slope of your function is always going to be negative. So you could write that down as f prime of x is going to be less than or equal to 0 It's going to be decreasing. Now, the next part that's going to help us out with evaluating the functions is we're going to go over concavity. Now, let's just write this in here. So, to start off, let's ask, what is concavity? So, concavity is, think about how when you take your x and y points and you take the derivative, right, you're getting the rate of change of those points, right? But so concavity, what this is going to tell us is the rate of change of the slope, right? So I'll write this down. So it's going to give the rate of change of the slope, right? So what exactly does that mean? Like, how can you mathematically describe it? So essentially what this is going over is the second derivative of x, right? And so what we need to know about that is kind of like how we did before when we were trying to figure out whether a function's increasing or decreasing. If the second derivative of f of x is going to be greater than 0, then that means that it's going to be concave. And then if you take the second derivative of f of x and it's less than 0, that means that's going to be convex. What that looks like graphically is, with concave, it's kind of, I don't know how to explain, but it kind of looks like a big hump, like a big hill going up, right? So kind of like this, right? And then you could even bring it over here if you wanted to. Oh, my bad. Hold up. Mix this up. Other way around. Like this. Concave. This one kind of looks like a downward little slope here. Or you could think about like, oh, this is a cave. You can put some rocks in here or something like that. Right? I don't know. Whatever helps you remember it. And then convex, this is the one that points up with the hill. Right, like that. And then combining those two together, we'll now be able to start solving a couple functions and describing how it changes over time. So let's get in with our first example problem here. So the first one we're going to go over is the function y of 1/3 x cubed minus 2x squared plus 3x plus 4. And what we want to know about this function is the first part. We want to know the interval where it's increasing and decreasing. And then the next thing we want to know is then our interval of where it's concave and convex. Interval of concave and convex. So the first thing that we want to do when we start tackling a problem like this is we want to find the derivative, right? Because we know if we want to address part A is where we want to find where it's increasing or decreasing, we know we need the derivative of the function. So if we remember when we want to find the derivative of a function, I'll go over this. D over dx of x to the n, you gotta remember that this is just n to the x, n minus 1, right? Remember that, we gotta use that, it's the power rule, right? So if we take the derivative of the function, we're gonna end up with x squared minus 4x plus 3, right? And then what we're gonna do afterwards is we're gonna set this equal to 0, right? And then we can see, can we factor this? From what it looks like here we are able to factor it. So we get x minus 3, x minus 1, right, as factors. And then if we solve for it, we get that what sets this function equal to 0 is 3 and 1, right? Those are going to be important, right? Because if we look back and remember, when our function is equal to 0, its derivative of the function is equal to 0. That's going to tell us that its slope is 0, which means it's either going to be a maximum or a minimum, right? Essentially what that's saying is that's going to be a critical point of the function, and we're going to need to remember that. So now after we've gotten that, we're going to now point this on a number line and then test points to see what's actually going on around these critical points. And that's going to help us go through part A. So if we start making this graph here, I'm going to start at 0. Get rid of this other point. Now let's just change the color here. I'll put this to a darker red. Might be easier to see. So we're gonna mark our points on our number line here at 1 and 3. Now what we're gonna do here is we're gonna grab this whole little part here where we broke it down. All right, let's see, we'll find a good spot to put this. I'll put it here for now. All right, x minus 3, x minus 1. And we're gonna start plugging in x values around on our number line to test what the sign value is of it. So to start off with, let's test like -3, right? So if we do -3 minus 3, we're gonna get a negative number, right? And then if we do -3 minus 1, we're gonna get another negative number, right? So let's put this right here at the top. Let's erase this bottom part here. So if we multiply these two values together, we're gonna end up getting a positive value. So keep that in mind there. Now, if we go over to the next part, let's say a value in between 1 and 3, right? Let's say we grab 2. If we grab 2, then our first one, 2 minus 3, that's going to be negative. Let's put this here. But 2 minus 1, that's going to be positive, right? So overall, the value of this sign is going to be negative, right? And then if we grab any number above 3, right? Since I have it on the number line, we'll just go with 4 here. We're going to get 4 minus 3, it's positive. And then 4 minus 1, that's also positive. So we can put down that both positive, and of course, positive multiplied by positive. Oh, hold up. Erased itself there. But that's going to give us another positive, right? And then I don't know if you see a trend here, but what happens when you do sign analysis on a number line graph is that you're going to have alternating signs. So here, let me highlight it. If you can see here, see positive, negative, positive. It doesn't matter any function that you do, the signs are going to end up alternating. But if you're like in the middle of a test or a quiz or something like that, you want to make sure that you put down that you at least evaluated all the different points before you jump to the conclusion that, oh, it's alternating, even though we all know that it's alternating. So let's get to the next part of this. So let's say what's going on here, but on an interval. So what we can conclude from what we just grabbed here is from -infinity all the way up to 1, right? But I'll get into the explanation part in a second. Let's just write it down. So from -infinity to 1, and then we have 1 to 3, and then from 3 to infinity. Notice how none of these points are included with the 1 and the 3. Of course, with the infinity values, you don't put it included because I don't know why, but you just don't. But none of these points are included because if you actually evaluate there, remember those are going to be our critical points. So we can't really say what's going on exactly at that point because it's 0. So now, what can we say about that? At these points, zoom in here, our derivative of the function is going to be greater than 0. And then here, derivative of our function is going to be less than 0. And here, like the other one's going to be greater than 0. Now, if we go back to what we remember before, when our derivative of our function is going to be greater than 0, what do we remember about that? Well, with our first derivative, if it's greater than 0, that must mean that our function is increasing. And then similarly here, that must mean that our function is decreasing from 1 to 3. And then it's going to be increasing again from 3 to infinity, right? And so now if we graphically think about this, right, remember we're trying to find the maximum and minimum values, right? Because we know that 1 and 3 are going to be critical points, right? But we can't figure out what type of critical point, right? So now that we've gone through this, I'll stick up this color. What we can now say is that it's increasing from here, right? And then all of a sudden, somehow, it's gonna start decreasing, right? And it's gonna start increasing again. So what we need to know is that whenever you see a function swap from increasing to decreasing or decreasing to increasing, that must mean that at some point our function, like our derivative of our function, is going to equal 0, which means it's either a maximum or a minimum. Now, if it goes from increasing to decreasing, that means that you're going to have a maximum point. But if it goes from decreasing to increasing, that means you're going to have a minimum point. So that means right here, let me write this down below. At x is equal to 1, we're going to have a maximum. And then where x is equal to 3, that means we're going to have a minimum. Hold on, let me write this. Oh, dang. Messing up my m's. One second. All right, good. Now that we've gone over that, we need to get the second part of what we need to evaluate. Because right now, we just got part A, right? We could go ahead and highlight this. We could be like, boom, done. Smiley face. So now we need to go over part B. We need the interval of where it's concave and convex. So, also another way that some teachers may describe it is they might say concave up or concave down, right? It doesn't really matter too much, right? Because concave, convex is easier to think about in my head, and I guarantee your teacher will accept either one. But back to what I was saying here. So we need to evaluate the second derivative. And if we remember, the second derivative just tells us the rate of change of the slope as it's progressing, right? And it's going to tell us, as I just said, if it's concave or convex. So if we go back, look up with our derivative of our function, right? We're going to take the function before we factored it because that's going to be easier. So swap the color back. We remember that the derivative of our function, y prime, was x squared minus 4x, was it plus 3. And so if we take the second derivative of our function, we're going to get 2x minus 4, right? And so just like how we did before, exactly the same, we're going to set this equal to 0 and start solving for it. Now we see what can we do. This one, it just looks like we're just, not 3, it looks like we're just going to solve it. And then when we solve it, what do we get? We get that our critical point is going to be at 2, right? So we're going to keep that in mind. And now we're going to move on to making our number line, right? It's exactly like how we did before when evaluating it for when it's increasing or decreasing. All right. So 0, 1, 2, 3, 4. Here it is. 1, 2, 3, 4, right? Swap the colors to make it a little bit more bright. So we evaluate it here. We know that there's going to be some type of critical point going on at 2, right? But not in the type of critical point where it's going to be a maximum or minimum. We'll get into that in a minute. So exactly like how we did that before, we're now going to grab our second derivative function, right? Our 2x minus 4, right? And we're going to start plugging in some x values below and above 2 to see what our sign value is. Remember, we're doing sign evaluation. So say let's just plug in 0 into our second derivative. We get 2 times 0 minus 4. What is that? A negative number, right? So we can say from there, our second derivative is going to be negative. Now let's plug in, say, 4, right? So 2 times 4, that's 8. 8 minus 4, doesn't matter what the value is, it's going to be positive. And just like how I talked about before when we were evaluating if it's increasing or decreasing, see how the sign value is changing? We have a negative next to a positive. Let's keep that in mind. And so what we can say here is that all the way up until 2, it's going to be like this. It's going to be convex. And then from 2 all the way to wherever, it's going to be concave, right? Because, you know, when it's negative, it'd be like that. Oh, hold up. My bad. Didn't want to explain that wrong. This is actually going to be the other way around. There we go. I accidentally flipped it in my head. Like that. Or did I put it right? I don't know. Maybe I put it right the first time. I don't remember. But this is how it's supposed to look, right? So now we have all that. Let's get our interval now of where it's going to be convex and concave, right? So we have from negative infinity up till 2, and then we have from 2 till infinity, right? So now what can we say when evaluating it? That means our second derivative from negative infinity to 2, this is going to be less than 0. And our second derivative from 2 to infinity is going to be greater than 0, right? So this means that this one is going to be convex. And this one's going to be concave, right? Now, we can highlight this and say, boom, we're done. That's all that the problem asks. But if you have an application problem where it's like, oh, now can you start graphing what the function looks like and what it may look like, all you would do is just take all the stuff that we just grabbed here, where it's increasing, decreasing, where it's concave, convex, put that together, maybe test a couple more points just to see how it looks, and then you could fully put together your function. That's all we need to know for that problem. And then we'll go over one more example problem here, just to clarify and make things a little bit more easier. So let's do this with a couple less steps to make it a little bit easier to remember. It's going to be example 2. Let's say that y is equal to 1/4 x to the 4th minus 3x cubed plus 2. Right? So if we remember from before, our first step is going to be finding the derivative of our function. And if you remember that, we're just going to use the power rule. So we multiply this, subtract that. It's going to be x cubed minus 9x, right? Now, what do? Well, we're going to set this equal to 0 for start off. But what I'm thinking here is I want to factor out an x to get x parentheses x squared minus 9. And this is going to be equal to 0. Because I see here that this is the difference of squares on this inside functions. So I'm able to do x minus 3, x plus 3 is equal to 0, right? And this is going to tell us that our critical points are going to be at 0, 3, -3, right? And then here, I'll just star this. And now the next part, remember we need to evaluate our number line at those given points. Right, so let's write down our number line. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right. Now after that, we're going to place down our points. Right, so if we remember, it was at 3, 0, -3. Now, just like how we did before, let's start evaluating the sign of our function at those given points. And let me just bring this down here, just to make it easier to see. So let's evaluate the function at numbers less than -3. If we go from here, what we get is that our x, of course, that's going to be negative. And then our x minus 3, that's going to be negative. And then our x plus 3, that's also going to be negative. So if we combine all this together, multiply them, what are we going to get? We're going to get that this is going to be negative for the sign. Right, so if we do the same thing here, we're going to get negative, negative, positive. Right, we're going to get positive, negative, positive, 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 positive. Just like I was telling you before, you know, the signs are just going to alternate. So I won't waste any time going over that. But if you want to really break it down, remember, we're just plugging in the values into this and then seeing what happens. Can erase this now. So now, like before, we're going to get the interval, right? So we know from negative infinity to 3, -3. It's this. And then we're going to be from -3 all the way up to 0. And then we're going to be from 0 all the way up to 3. And then we're going to be from 3 up to infinity. So what do we know here? We know that the second derivative of f of x is going to be less than 0 right there. The second derivative of x is going to be greater than 0. And then, as I said before, it's just going to alternate. So we're just going to write this down a couple more times. So if we remember, if it's less than 0, that means it's going to be decreasing. Greater than 0, that means it's increasing. So we're just going to write these down. Oh, my bad. Not the second derivative. It's going to be the first derivative. This here, I'll fix this up. Our first derivative. There we go. And then increasing. Now here's where we get the second derivative. I was getting ahead of myself a little bit. So we're going to take our first derivative function, which is x cubed minus 9x, and then we're going to take the second derivative of it. So what do we do here? All we got to do is then make this 2x. No, my bad, not 2x. 3x squared minus 9, right? And then we're going to set this equal to 0. And then when you do that, you're going to end up with x is going to be equal to plus or minus √3. And like how we did before, we're going to plot this on a number line. Put 0 here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then root 3, it's about 1.6-ish. So that's going to be about here. And then negative root 3, that's going to be about negative 1.7-ish. So just to make this clear, I'll put an arrow here. It's going to be negative root 3. It's going to be positive root 3. And now, just like before, we're going to start evaluating our function at these points. This here. Actually, no, I'll stick with the pink. So if we plug values in here, let's plug in negative 3. Negative 3 squared, that's going to be 9. 9 times 3 minus 9 doesn't really matter. All we need to know is that our function below this point is going to be positive. And then we'll plug in some stuff in the middle. Let's plug in, say, 0. 0 squared, that's 0. 0 multiplied by 3, 0. 0 minus 9, negative. Plug in some stuff beyond root 3. Let's say, like, I don't know, 3. It's going to pop out the same as when we did it for negative 3. So we know that's going to be positive. Right? So now we need to get the interval of what's going on at this function. So from negative infinity to negative root 3, and then to negative root 3 to root 3, then over to root 3 to infinity, right? And so what we can say here is the second derivative of f of x is going to be greater than 0. The second derivative of f of x is going to be less than 0. Then the second derivative of f of x is going to be greater than 0 from here, right? So if we remember, if our second derivative is greater than 0, then this is going to be concave. Less than 0, convex. And then same like the first one, this is going to be concave. So if we look at it like with the little humps like I was showing before, it's going to be like this, then like this, and then it's going to be like this. Now, this kind of makes sense with our function, because if we go back and look at our our regular f of x function, we can see that's the 4th degree polynomial, right? So if we remember our 4th degree polynomials, the two end parts, like the end parts of your polynomials, always face the same direction. And since there's no negative on our leading coefficient of our polynomial, we know that whatever's going to happen in the middle doesn't matter. But we know that these two end parts, here, let me use a highlighter, hold up, are going to be facing up, right? So erase this real quick. That matches with what we have with our convex and concave little number line graph we see here, which you can kind of tell with when I added in the little hump parts. You can kind of see, say like I just extended this out, added some lines here. You can kind of see how that looks like a normal x to the 4th function, right? So just like how I said with the previous problem, you could put it together and start evaluating, what does our graph actually look like, and what is this and what is that? And I don't know, maybe I'll get into that later. But as of now, that's all the stuff that I have to go over. And that pretty much covers everything that's going on with 5.3, except the really nuanced technical stuff. But really, if you're able to do this with finding your first derivative, evaluating it on the number line, then your second derivative, evaluating on the number line, and then being able to say on the interval, right, of where it's increasing, decreasing, concave, convex, what's going on there, then you're looking really good for at least this section for calculus. And that's it. Have a good day.